A ghost ship of the cosmos, a defunct satellite tumbles silently at 27,000 kilometers per hour. Note is not just a relic. It is a ticking time bomb. A single collision could shatter it into a cloud of shrapnel, a lethal swarm of debris threatening the International Space Station and the very satellites that power our world. Popular culture whispers of a secret NASA mission, a high-tech capture ship that could appear out of nowhere to sweep these orbital ghosts away. But the true story is far more compelling. This is not a tale of a single hidden device, but a dramatic saga of decades of rivalry and collaboration, of breathtaking advancements in robotics, and a high-stakes international legal battle that will define the future of space for all of humanity. The secret isn't hidden. It's waiting to be discovered, in plain sight. If you've ever imagined a clandestine department at NASA, a place where hidden technologies are guarded by a veil of secrecy, you're not alone. But the truth is, the agency's handling of classified information is not a shadow operation. It is governed by a strict, publicly available legal framework. This bureaucracy of regulations is not a cloak for concealment, but a robust mechanism for safeguarding information in a controlled and systematic manner. The very existence of these public documents serves as a check on clandestine operations. The legal foundations for this are codified in documents, such as the National Aeronautics and Space Administration Federal Acquisition Regulation Supplement. This supplement mandates that any contractor or subcontractor who handles unclassified electronic information for NASA must protect its confidentiality, integrity, and availability. A key piece of this public paperwork is the DD Form 254, or Contract Security Classification Specification. This legal document is a requirement for all classified contracts and publicly outlines security requirements, classification levels, and access guidance. Its existence makes secrecy a defined and documented state, not a hidden condition. NASA's public response to speculation about unidentified anomalous phenomena, UAP, is a perfect case study in this transparency. The agency convened an independent study team to provide a roadmap for the scientific analysis of UAPs. The team's report found no evidence of extraterrestrial origins for UAP, emphasizing instead that the main obstacle to understanding these phenomena is the lack of consistent, detailed, and curated observations. By appointing a director of UAP research, NASA is actively working to reduce the stigma around reporting such incidents, positioning itself as a trusted, scientifically open authority. This deliberate strategy directly counters the very speculations that give rise to the idea of a secret. The real story is a transparent bureaucracy, a legal fortress of public information that stands in direct opposition to the concept of a single hidden secret. The discipline of capturing spaceships is formally known as rendezvous proximity operations and docking. This fundamental capability was not born of a secret discovery, but of a public technological race between the United States and the Soviet Union, a rivalry that began in the mid-1960s. The United States pioneered the human-centric approach. On March 16, 1966, Gemini 8 astronauts, Neil A. Armstrong and David R. Scott, performed the world's first docking, a manual feat of piloting skill that was publicly celebrated and televised. Manual docking was later a critical component of the Apollo program's lunar missions, requiring astronauts to dock the command and service module with the lunar module both en route to the moon and after the lunar landing. In contrast, the Soviet Union focused on automation from the outset. The first successful automated docking occurred on October 30, 1967, when two uncrewed Soyuz test vehicles connected in orbit. This automated approach later enabled uncrewed Progress cargo spacecraft to autonomously resupply space stations, a capability that extended mission durations and was crucial for the Salyut program. The history of RPOD is a matter of public record, a progression of innovation that culminated in a moment of international cooperation, the Apollo-Soyuz test project in 1975. This mission required a specially designed docking module to accommodate the different systems of the U.S. Apollo and Soviet Soyuz spacecraft, proving that open, interoperable systems were more valuable than preserving national secrets. The concept of a capture spaceship has evolved into a portfolio of advanced robotic technologies designed for on-orbit servicing and debris removal, all of which are publicly documented. The purpose of these missions is not secretive, but driven by a clear economic and strategic need to extend the operational life of satellites, refuel them, and perform in-orbit repairs. A famous and non-secret example is the Canadarm, formerly known as the Shuttle Remote Manipulator System. This remote-controlled arm was a general-purpose tool used on 90 space shuttle missions between 1981 and 2011, deploying and capturing satellites and positioning astronauts. Building on this legacy, modern systems like the NASA Robotic Servicing Arm are highly specialized 7-degree of freedom manipulators designed for autonomous capture and dexterous operations. This arm's lineage can be traced to systems used on Mars rover missions and flight-qualified robotic arms developed under the Defense Advanced Research Projects Agency. This technology is integral to the publicly announced OSAM-1 on-orbit servicing, assembly, and manufacturing mission. To accomplish a secure capture, these arms are equipped with specialized gripping mechanisms. The robotic gripper, developed at NASA's Goddard Space Flight Center, is designed to autonomously or remotely grasp a satellite. This device interfaces with a standard separation ring and, once engaged, constrains all 6 degrees of freedom of motion between the servicing spacecraft and its client. The complexity lies not in a secret component, but in the precision engineering and software required for the sensors to confirm the distance, orientation, and velocity are within an acceptable range. The development of these capabilities is a product of extensive public-private and interagency collaborations, a shared multinational endeavor aimed at creating open, interoperable systems to solve a global problem. While docking with a cooperative spacecraft is a well-established capability, the greatest challenge is the capture of uncooperative or defunct objects, such as a tumbling, powerless satellite. The real secret is not a perfected technology, but the immense difficulty of this problem. A derelict satellite is a complex technical challenge because it lacks active thrusters for stabilization and may be spinning uncontrollably, much like a child that won't sit still. This tumbling motion makes a safe capture exponentially more difficult, as the chaser spacecraft must precisely match the target's rotation and translation. The force and momentum transferred during the collision between a robotic arms gripper and a tumbling target can cause complicated dynamic behaviors, including vibrations in the arm's flexible links. Human control from the ground is often not feasible due to time delays in orbital communication, which can exceed a 1-second round trip. This necessitates the development of highly sophisticated autonomous guidance, navigation, and control systems that use advanced sensors such as LiDAR and cameras to track the target's position and orientation. The public and experimental nature of this research is best exemplified by the Remove Debris mission, an in-orbit testbed for technologies to address space junk. This project, co-funded by the European Commission, openly tested several different capture methods. The mission's success was not a secret, but a publicly announced milestone. The NET experiment successfully captured a simulated piece of debris. Furthermore, the Harpoon experiment successfully fired a harpoon at a target penetrating it at a velocity of 20 meters per second. The public documentation of these successful but limited tests demonstrates that a final secret solution does not exist. Instead, the field is one of active, public, and experimental development, with researchers openly publishing their findings and discussing the challenges.
Even if a perfectly engineered, quote, capture spaceship existed, its widespread use would be severely limited by an outdated and ambiguous international legal framework. The most significant barriers to orbital capture are not technical, but legal and political. At the heart of this issue is the Outer Space Treaty of 1967. Article 8 states that a space object remains the property of the launching state while in space. This creates a legal paradox. A piece of space debris remains the property of its owner, and there are no salvage rights in orbit. This means that a, quote, capture spaceship could not legally remove a piece of another nation's debris without explicit permission, a major political hurdle. The legal ambiguity is further compounded by the lack of a clear legal definition for space debris itself. As of 2006, no international agreement or UN document had formally defined the term. This institutional gap makes it impossible to establish clear rules of the road or assign liability in the event of a collision. The 1972 Liability Convention, which was intended to define negligence in space, is neither straightforward nor enforceable and fails to answer critical questions of fault and causation. The legal framework was established when only a few states had significant space capabilities. Today, with the proliferation of state and commercial actors, these laws place an overwhelming degree of liability on states for the actions of private companies. The resolution of this issue requires diplomatic efforts and a global consensus, not a technological breakthrough. The user's query for a NASA secretive capture spaceship is predicated on a beautiful but false premise. The investigation reveals that the capabilities and technologies for spacecraft capture are not secret, but are a matter of public record, historical fact, and ongoing collaborative scientific research. The most profound insight is that the true secret is not a clandestine piece of hardware, but the complex, painstaking, and collaborative effort of thousands of engineers, scientists, and legal experts to make these feats possible. From the publicly broadcast manual docking of Gemini 8 to the open-source data from the Remove Deborah's mission, the history of spacecraft capture is a testament to open innovation. The NASA Robotic Servicing Arm, a cornerstone of future orbital servicing missions, is a product of multi-agency and international collaboration, demonstrating that the future of space lies in shared knowledge, not hidden secrets. The most significant barriers to widespread debris removal are not technological but legal and political, requiring diplomatic solutions rather than engineering breakthroughs. This article demonstrates that a speculative conspiratorial narrative pales in comparison to the rich, documented, and very real history of space exploration. The secret is that the true story is more compelling than the myth, and that the continued progress of humanity in space depends on transparency, public investment, and international cooperation. The legal and political barriers to orbital cleanup are no longer abstract theories. They are playing out in real time with profound and dangerous consequences. Over the past 2 decades, several nations have demonstrated a different kind of capture capability, the ability to intentionally destroy their own satellites with anti-satellite IFLA weapons. In 2007, China's People's Liberation Army successfully destroyed a defunct weather satellite, the Fengyun-1C, at an altitude of approximately 860 kilometers. This single act of aggression against its own property created over 35,000 pieces of debris larger than 1 centimeter, which will remain in orbit for decades due to the high altitude. This cloud of shrapnel immediately increased the risk of collision for hundreds of other spacecraft, including the International Space Station. Similarly, a Russian test in 2021 against its own satellite, Cosmos 1408, created over 1,500 trackable pieces of debris and a cloud of hundreds of thousands of smaller fragments directly endangering the crews on the ISS and the Chinese space station. These destructive tests highlight a geopolitical problem that a simple legal framework cannot solve. While Article 9 of the Outer Space Treaty condemns harmful contamination, it lacks the enforcement mechanisms to hold nations accountable. The international response has been a mix of public condemnation and a call for new norms. U.S. officials described Russia's action as dangerous and irresponsible, while countries like the United Kingdom, Japan, and Canada issued formal protests against China's test, calling it irresponsible and contrary to the peaceful use of space. These events have galvanized international efforts to ban intentional debris-creating actions. The European Space Agency has even spearheaded the Zero Debris Charter, a voluntary initiative that aims to have all new space missions be debris-neutral by 2030 by reducing intentional debris release and improving end-of-life disposal success rates to over 99%. This new, urgent reality has given rise to a bold new class of pioneers, private companies. These aren't government agencies bound by decades of legal precedent, but agile startups funded by both public and private capital. The European Space Agency, for example, has contracted with a Swiss startup called ClearSpace SA for the ClearSpace-1 mission, a project that will use a four-armed space claw to capture and deorbit the defunct Probo-1 satellite in 2026. In a similar vein, the company Astroscale, a leader in on-orbit servicing, is developing missions like ELSA-D and COSMIC to prove the viability of a circular space economy. Their technologies, which include magnetic docking and robotic arms, are designed to extend the lifespan of satellites and eventually remove inactive ones, ensuring a cleaner orbital environment for everyone. Yet, the story of space remains intertwined with secrecy. While these commercial ventures are publicly announced and transparent, the military dimension continues to operate in the shadows. The U.S. Space Force's X-37B orbital test vehicle, a reusable and autonomous spaceplane, flies missions whose payloads and objectives are often highly classified. While some publicly known experiments involve laser communications and quantum sensors for navigation in GPS-denied environments, the full scope of its capabilities remains hidden from view. This creates a compelling paradox. A new generation of commercial pioneers is openly working to build a sustainable future in space, while the world's major powers continue to develop and test their most advanced technologies behind a veil of secrecy. The secret of a capture spaceship is not a single device, but a dynamic and at times dangerous competition of innovation, diplomacy, and ambition that continues to unfold in plain sight.